Welcome to this explainer. Today, we're taking what usually feels like a massive, daunting engineering headache and turning it into a clear, empowering blueprint for true energy autonomy. Sizing an off-grid solar system correctly is the absolute foundation of reliable power. It ensures you aren't overspending on unnecessary components while still making sure the lights actually turn on. And we're starting this journey with the ultimate winter survival test. Because think about it, what actually happens when the sun just doesn't shine for 3 whole days? Setting this worst-case scenario right out of the gate is absolutely crucial. It proves that doing the math right from the very beginning means the difference between freezing in the dark or living comfortably, totally off the grid. It's really not just about capturing sunlight, it's about capturing certainty. So here's our 6-step blueprint to get there. We'll analyze the loads, select battery voltage, determine days of autonomy, calculate battery size, find your sun hours, and finally calculate solar panel requirements. Let's jump right in. All right, step 1, analyzing the loads. We've got to build this system from the foundation up, right? And that means figuring out the total daily watt hours for literally every single DC and AC device you plan to run. Think of it as a deep dive energy audit. You need to jot down every light bulb, every laptop charger, the whole shebang. But here's the kicker. You've got to account for duty cycles. Just because an appliance is plugged in all day doesn't mean it's drawing power all day. Take a standard 100-watt fridge, for example. It doesn't run 24/7. The compressor is really only active about 30% of the time, so it's truly only consuming power for roughly 8 hours a day, not 24. Understanding this simple concept keeps you from completely overestimating your daily needs. Oh, and you definitely need to watch out for inverter standby power. This is a sneaky little phantom dream that eats up energy just by being turned on. See, if you have AC devices, you need that inverter to swap your battery's DC power to AC, but doing that takes a toll. A standard 1,000-watt inverter might constantly pull 20 watts just sitting there on standby, and larger hybrid models, they can siphon off up to 50 watts around the clock. You absolutely have to factor this invisible drain into your total daily consumption. Once you add up all your devices plus the standby load, you've got your total daily energy requirement.
Okay, moving on to step 2, selecting battery voltage.
This is the engine of our system. The main goal here is to keep our current under 100 amps. Why? Because it dramatically cuts down on the need for super thick, expensive wiring, and it boosts the overall safety and efficiency of the whole setup. To do that, we match our battery voltage to our inverter wattage. If you've got a smaller inverter under 1,000 watts, a 12-volt system works perfectly. Stepping up to that 1,000 to 2,000 watt range, you're going to want a 24-volt system. And for those massive whole cabin setups running up to 5,000 watts, you definitely need to be designing a 48-volt system. Nailing this from day one saves you so many headaches down the road. Next up is step 3, determining days of autonomy. This right here is our safety net. We're figuring out exactly how long your entire system can survive on battery power alone, without a single drop of sunshine hitting those panels. And in the off-grid world, there's a golden rule, the number 3. You need 3 days of autonomy to comfortably weather back-to-back cloudy or stormy days. Sure, if you're just building a grid-tied system where solar is a backup for a quick neighborhood blackout, 1 day is usually plenty. But out in the wild, totally disconnected, 3 days is the magic number for absolute peace of mind. Which brings us to step 4, calculating battery size. Welcome to the great battery battle. Here, you take the total watt hours we just calculated and divide them by your chosen voltage to find your required amp hours. But when you contrast the two main battery chemistries, you get this massive aha moment. Just look at the numbers. Lead-acid batteries, they really only give you about 50% usable capacity and run at roughly 80% efficiency. Since draining lead-acid battery past halfway literally damages it, you end up having to buy a massively oversized bank just to make the math work. But lithium batteries are a whole different ballgame. They run at 99% efficiency and offer 80% or more usable capacity. That means your lithium bank can be way smaller, way lighter, and much more compact while delivering the exact same amount of usable power. All right, step 5, finding your sun hours. Now that we've got our consumption and battery size locked in, we need to prepare for the darkest month of the year, which is usually December if you're in the Northern Hemisphere. We do this by pulling our local sun hours from online tools like PV Watts. But listen, it is so crucial to remember that sun hours does not mean hours of visible daylight. If the sun rises at 7 a.m. and sets at 5 p.m., you do not have 10 sun hours. Sun hours refer strictly to concentrated peak solar energy. It's the exact measurement of that intense, direct energy you need to actively push a heavy charge back into your battery bank. To put this into perspective, with a real-world worst-case scenario, let's look at Houston, Texas. Even down south, in a relatively warm climate, Houston only averages 3.47 peak sun hours in the dead of December. That is your actual operational window. You have less than 3.5 hours of peak energy to do a full day's worth of heavy lifting. And that leads us right into our final step. Step 6, calculating solar panel requirements. Here we need to figure out exactly how many solar panels it takes to act as the massive hose that'll completely refill your battery tank during those super short winter days. It all comes down to your daily recharge requirement. Because different batteries let you empty the tank differently, your math shifts. With lead acid, you're only ever replacing the top 50% of the capacity that you depleted. But with lithium, you might be utilizing a much larger swing, say drawing it all the way down to 10% and needing to blast it back up to 90. So, whatever your specific daily energy requirement is, you simply take that number and divide it by your lowest winter sun hours, like that 3.47 we just talked about for Houston. Boom. The result is the exact final solar wattage your roof or ground mount needs to support. And honestly, the absolute beautiful payoff to all this math is that sizing for your winter minimum guarantees year-round autonomy. If you meticulously follow this blueprint and your system is mathematically bulletproof for the harsh, short days of December, well, it's going to provide effortless, overflowing energy all summer long. You'll literally have power to spare when the days are long because you built an unbreakable foundation for when they're short. So that wraps up our design process. You've audited your loads, selected the perfect voltage, secured your days of autonomy, sized your batteries, hunted down your sun hours, and calculated your panel array. Now that you hold the blueprint to true energy autonomy, the only question left is, where are you going to build it? If you can engineer absolute certainty in the darkest month of the year, what other off-grid boundaries are you ready to push? Thanks for hanging out with me for this explainer, and I hope this gives you the confidence to start building your own autonomous energy system today.